Okay, till now, the CPM modeling we have previously discussed are all based on the continuous conduction mode. So you might be curious about what if the topology operates in discontinuous conduction mode. So in this section, we are going to study how can we model the DCM mode CPM controllers. So before we talk about the detailed modeling methods, let's first have a look at the features of the DCM CPM modeling. So the first feature is that the CPM DCM model maintains a single pole response, right? So single low frequency pole. In the transfer function. So indeed there is also a second pole, but the second pole, which mainly is induced from the inductor, so we call it the inductor pole, is pushed to high frequency. And also the right half plane 0 are both pushed to high frequency, which is even higher than the switching frequency. Mainly due to the small L, right? So as we previously mentioned, for the DCM operation, the inductor current ripple is large and the inductance is usually small. So this small L will push the inductor pole and also the right half plane 0 to very high frequency. And secondly, for DCM boost and back boost topology, so they are naturally stable without the ramp. So this means that we no longer need to insert the artificial ramp to the controlling signal, right? So ramp compensation is no longer required for the DCM boost and back boost. And thirdly, for back, right, DCM back, we still need to have the ramp compensation. So under CPM, so it is stable without ramp. If the duty cycle is below 2/3. Remember, when we talk about the CCM, right? So the back is stable only if the duty cycle is below 1/2. So the stable range is extended, right, from 0 to 0.5 to 0 to 2/3. And so for back, we still need to add the artificial ramp, but the ramp will be relatively small. So a small ramp can be added, and which leads to stability for all duty cycle. Okay, so that's the general features, right? Next, I will lead you to show the detailed derivation processes. So first, let's look at the buck boost example, right? So let's see how buck boost can operate without ramp and achieve stable. So now let's look at the buck boost example. So first, let me plot a schematic of the buck boost converter. So here is the input source and the input voltage VG. And here is the switch Q. And here is the inductor L. Here is the diode D. And the filter capacitor C. And load resistor R. So here is the output voltage. So for this buck boost topology, we can extract its switching network. So here is the switching network, Q and D. We can mark the quantities for this two-port network, right? So here is I1, and this is the input port voltage, V1. And here is the I2, and here is the output port voltage, V2. So the L is excluded from the switching network, right? So switching network. So based on the buck boost circuit, we can plot its critical current waveforms. So say that here is the controlling signal IC, and let's say we insert a ramp here, right? Let's say we insert a ramp. So here is TS. And the ramp slope is minus MA. Now let's plot the inductor current waveforms. So because this is discontinuous conduction mode, so inductor current will begins to rise from 0, right, when the switch is on, and then rises linearly at slope of M1. When it hits the ramp compensated controlling signal, then the switch is off, so the current begins to drop at minus M2. And when it hits 0, it will remain 0 until the next switching cycle is triggered. So basically, here is the duty cycle, right? D1, TS. So for this critical waveform, right? This is IL. So for the mode 1, the Q is on, right? Q is on, meaning that the inductor voltage is equal to the input voltage. So the slope of the inductor current will be equal to the input voltage divided by L. So here we consider small ripple approximation. So we only consider DC part. So we use capital VG here. And for buck boost, right? So the input port voltage is V1. So we can apply KVL to this loop, right? For average voltage, the inductor has 1-second balance, right? So meaning that the inductor average voltage is 0. So that the average input voltage of this switch network will be equal to the average of the input source voltage. So we can write that this is equal to average V1 over L. And secondly, let's look at M2. So M2 is the slope of inductor current when the Q is off, D is on, so that the voltage across L will be equal to the output voltage, right? Output voltage. So M2 will be equal to minus output voltage over L. Again, we can apply the KVL to this loop due to the Bose-Einstein balance to the inductor. So inductor average voltage is 0. So this average voltage should be equal to this output average voltage. So we can write this as average V2 over L. Thirdly, let's look at the peak current here. So we denote this as I peak. So I peak can be found from here to here, right? The slope is M1. So I peak can be easily derived by the slope times the base. So M1 times the base is D1 TS. And based on the I peak, we can extend to here. And starting from this right angle triangle, we can derive approach to IC. So IC will be equal to I peak plus this base, right? This base. So this base, because this line has slope of minus MA, so this distance will be equal to MA times the duration, D1 TS. And we can insert I peak to here and extract the common part, right? D1 TS. So this will be M1 plus MA times D1 TS. So therefore, we can derive that D1 equals to D1T equals to ICT divided by M1 plus MA TS. Then next, we can do the average switch modeling as what we did before. So we look at the input port, port 1. So the I1 average, this current average, will be, so I1 will have this shape, right? Shape. So I1 will be equal to the area of this triangle divided by the entire period. So the area of the triangle will be easy to be calculated as 1 over 2 times the base times the height. Height is I peak. Base is D1 TS divided by TS. So TS cancels. So it's just 1 over 2 I peak D1, right? And we learned that D1 I peak, right, equals to this M1 D1 TS. So this will be 1 over 2 M1 D1 square TS. Then we can insert the expression of D1 to here. So this will be equal to 1 over 2 M1 times D1 square, right? D1 square. So D1 square is IC square times M1 plus MA square TS square times TS. So that the TS can again be cancelled. Here's removed. Here's the square is removed. Then we reorganize this expression. So this becomes 1 over 2. We multiply both numerator and denominator by m1 squared. So this is 1 over m1 times IC squared times fs. 1 over ts is indeed switching frequency. So here it becomes 1 plus ma over m1 squared. So this equals to 1 over 2 L times IC squared Fs times, right, because M1 equals to V1 average over L. So 1 over M1 equals to L divided by V1. So L divided by V1 average Ts times 1 plus MA over M1 squared. So the left-hand side is average input port current. And the right-hand side, you'll see that here is average input port voltage. We can move this to the left-hand side. So on the left-hand side, it will be the product of voltage and the currents. On the right-hand side is the left part, right? 1 over 2 L IC squared Fs divided by 1 plus MA over M1 squared. So you will see that the product of the voltage and current is indeed the power, right? So this is the average power absorbed from the input port. This means that the input port can be treated as a power sink. So which sink the power supplied from the voltage source and then transduce the power to the output port of the switch network. Okay, now let's erase the right-hand side of the blackboard. Okay, we have erased the right-hand side of the blackboard. So now let's look at the output port. As I previously mentioned, the input port behaves like a power sink. So the output port will behave like a power source. So this is mainly because the switch network cannot store the energy, right? So energy in should be equal to the energy out. So therefore, on the output port, so we'll have the I2 average times V2 average equals to the sinked power as I wrote it here, right? Same expression. 1 over 2 L times IC squared Fs divided by 1 plus MA over M2 squared. So this is again equals to the absorbed power from the input port. So for the output port, it is a power source behavior. And as what we previously process using the average switch modeling method, we can construct the DC steady state model for the buck boost converter in DCM and the CPM control. So DC steady state model. So the input port, right, average input port voltage. Switch network is modeled by a power sink with a power source. Here is the inductor. Here is the capacitor. Load resistor, right, L. And here is the output average voltage, V average. For the switch network, we mark their quantities by average value, right? So here is the flowing in average current for input port, and here is the average input port voltage, and here is the output port current. Here is the output port voltage average. So based on the steady state model in DC, we can calculate the output voltage, right? What is the output voltage? So for this model, the power source power will be equal to the average absorbed power from the resistor, right? Mainly because the average power for inductor and the capacitor at steady state should be 0. So based on the energy conservation law, this power source should be equal to this power. So for the output side, right? So the power absorbed from the resistor equals to V squared over resistance, right? So this should be equal to the DC steady state power source, right? So 1/2 L times DCIC squared Fs divided by 1 plus DCMA over DCM2 squared. So therefore, we can calculate the output voltage accordingly, right? Output voltage should be equals to square root power times resistance. Right, then we can insert the power expression to here to figure out what is the output voltage for CPM control in DCM operation. So IC over 1 plus MA over M2, M1 times square root load resistance times switching frequency over 2. So that's the DC model for CPM in DCM operation. Okay, so now let's erase the right-hand side of the blackboard. Okay, now we have erased the left-hand side of the blackboard. So previously we have derived the DC model. Now let's consider the small signal AC model. So the method is pretty universal. So we just, on top of the DC model, we insert the perturbation and the linearize, right? Perturb and linearize. Linearize means that we only keep the small signal, first order small signal AC terms, right? So for here, I just put the results since we have been doing this many times. Okay, so the obtained small signal model will be like this. So input port is input source, line input small signal, right? VG cap. And this switch network with power sink and power source, after linearization, we can model them by such a network. So virtual resistor, right? R1 in parallel with a independent source whose value is F1 times IC cap, and also a controlled current source as G1 times V2, right? V2, which is controlled by the output port. And for the output port, similar 3 items, right? One is the controlled current source, G2, V1 cap. And secondly is a independent current source, which is F2 IC cap, and also a virtual resistor whose value is denoted as R2. So that's the small signal model for the switch network. And for the others, we keep it as it is. So here is the inductor L. And here is the filtering capacitor C. And the load resistor R. So the input voltage for the switch network is V1 cap. And here is V2 cap. So the notation marks the polarity of the input and output voltage. Now let's look at the obtained small signal model. Because the DCM usually is associated with a small l, right? So L is small in DCM. So we can, if we consider the for frequency sufficiently lower than switching frequency, then we can consider that L is approximately considered to be short. So we can remove this L by replacing it by a well for approximated analysis. Then we can try to derive the transfer functions accordingly, right? First one we care about is control to output transfer function. So which is the output small signal divided by the controlling current small signal under the assumption that the line input is 0. So if the line input is 0, right, and L is short, so the V1 cap equals to VG cap equals to 0. So this current source will be equal to 0, which can be treated as an open circuit. So if here is open circuit, then the output voltage will only be impacted by this independent current source, whose value is F2 IC cap. So the output voltage will be just equal to F2 IC cap times R2 parallel with R, parallel with C, right? Divided by IC cap. So IC cap will be cancelled. So the results will be just equal to F2 R2 parallel with R parallel with 1 over SC. So you will see that there is only one S item here. So this will be a single pole response. We can normalize it to be the standard format of DC0 divided by the single pole response, 1 plus S over omega P. So where, after comparing this and this equations, we can list the expression for DC0 is F2 times R parallel with R2. And the omega P is the pole position, is determined by the time constant, which is the 1 over R parallel with R2 times the capacitance. And the next transfer function we care about is the GVG equals to output voltage small signal divided by line input under the condition that controlling input is 0. So for this time, right, the line input is no longer 0, but controlling input is 0. So here can be opened, right, because the current source equals to 0 amp. So the output voltage will only be determined by this current source, which is G2 V1, and V1 equals to VG, right? So this can be easily derived as G2 times R2 parallel with R parallel with C. And again, we can normalize, right? Normalize in the standard format equals to G0 divided by 1 plus S over omega P. So the pole position will be identical to the GVC because they are essentially the same, right? R2 parallel with R parallel with 1 over SC. Only difference is this coefficient, right? F2 and G2. So omega P is identical to here. And we just need to check the GT0. GT0 will be equal to G2 times R parallel with R2. So that's it. That's it. Okay. So in this section, we have started the modeling of DCM operation of the CPM controllers. So similar to the pulse width modulated control, so the DCM mode CPM controller also maintain simple dynamics. And the small signal transfer function only demonstrate a low frequency pole response. And the inductor induced high frequency pole and right half plane 0 are both pushed to high frequency. So for approximated analysis, we can consider that the DCM operated CPM controller essentially also maintain a single pole response. So this can significantly simplify the dynamics of the system.